Alright everybody, today we're back. We're going to be solving question 10, week 9, and the reason I'm going through this question in particular because I found two ways of solving it. Both are fine in their own right, but I think you can really learn something from these two solutions about buoyancy and mass and how it all really just ties in together. So we're going to start off with the more proper solution. So let's get to it. Let's draw the question out first, which is what I pretty much always do for physics questions, because it just helps you really understand what's going on. So I'll draw it out. So there you go. That's a pretty straightforward drawing. Here we have the coin in the middle, and we have its weight, and we have its apparent weight, or essentially what a person is recording in the question on their spring balance. So obviously there's a bit of mass that's displaced by water. Obviously if you're in a swimming pool or in the ocean, there's going to be a bit of mass that's going to be displaced. There's going to be a bit of upwards acceleration on you due to the water. That's why you feel lighter in a pool or in water. And the same thing applies to the coin. Well, the coin is much denser than you, so numbers are going to be slightly different. So what weight is displaced by the water? Well, that's a pretty simple calculation. It's just 49.7 take away 46.8, and that works out to 2.9 grams. There's an equation to solve this sort of question, and that's just P equals M over V. Now, I don't think this is actually a P. I think the name for it is rho, and it just denotes the density. Density when it comes to hydrostatics, like in this question. For this formula, we already have the mass, and we just need to really find the volume. So P, and the mass is just pretty straightforward. It's just 49.7 grams. But this is, when you're entering numbers into formulas, you want to use SI units, because it really it's a standard way of doing things, and it really helps you prevent mistakes and such. So we can just convert 49.7 grams to SI units, kilograms. The SI unit for weight is the kilogram, and there we have it. But the volume is a bit more tricky now. We have to give there's a bit of a leap conceptually here that you have to go through. Alright, my previous explanation wasn't great, so I'll redo it there. There's buoyant force of 2.9 grams. That means 2.9 grams of whatever liquid has been displaced. We know that water is 1 gram per cubic centimeter. Therefore, 2.3 centimeters cubed of water have been displaced. Over and converting centimeters cubed to meters cubed is really quite simple. Just remember your cube, because there's 100, 100, and 100. Right, so what we really need to do is just 2.9 over 100 cubed, and that is it. That's our volume in meters cubed, which we can just calculate to so 2.9 divided by 100 cubed, and that's our volume. So now that we've got our volume in meters cubed, we can just do 0.0497, which is the mass in kilograms. Then we can just divide it by our answer, and we get 17,137 kilograms per meter cubed, which is the density of the metal. And that's the first way of doing it. Alright everybody, now we're going to retake that. That's a fucking bad take. So now now I'm going to go through method 2. I think this method, understanding it, can also it can be pretty helpful and it ties into something called relative density, which is you would study in applied maths for a leaving cert. The way I think of the solution, to get a sort of overview of it, is I would imagine the coin to be the same density as the liquid. So if you have a coin and it's submerged in a liquid of equal density, then there will be no buoyant force. So that's when the density liquid equals density So when the density of the liquid equals the density of the object, then there is no buoyancy. Imagine if you had a water balloon filled with water and you put it in an aquarium or a swimming pool. There would be no force of buoyancy. So that's sort of the extreme. However, in this case, there is a difference in the mass of the object, or rather the density of the object and the density of the water, and we can calculate that pretty simply, which is just 2.9 over 49.7. Now, what do these two numbers mean? Well, I think it's sort of a ratio of one mass to another mass. So the ratio of mass of water compared to the ratio of mass of the coin, which gives us 2.9 over 49.7, which equals to 5.8%. So just like that, we can come to the conclusion that the water is only 5.8% as dense as the metal. Given that we know the density of the water, that gives us three things we know and one thing we don't, which we can put into equation to solve the one unknown. So if 5.8% equals to the density of water, and we can rewrite that as a number like that, then 100%, or just 1 in this case, equals to our unknown density. And we can solve for x, So in this case, we're just going to have to do 1 times 1,000 divided by 0.058, which gives us x equal to 17,241. It's a slightly different answer because I rounded through the question, but it is the correct way of doing it. It is a correct way of doing it. So that's how I done question 10 in week 9.